Good morning, everyone. My name is Siddharth Katare. I work as Senior Solution Architect with HCL Technologies. I am glad to be part of this tech webinar series organized by Same Israel. Today, I'm going to talk about IP development as a service and focus on creating designs which are beyond the standards. So these are the couple of things which we'll go through. One is we'll look at HCL at a glance, and then the concept of the chip design factory. Then what do we mean by design beyond standards? And then we look at a couple of case studies and examples where IP as a service plays a role. And then summary slides. So if you look at HCL has close to $11 billion revenue. And we have presence in 52 countries. And we have close to 200K entrepreneurs or the workforce, right? And then the engineering and R&D service, which caters to, for example, embedded softwares, hardware design and development, mechanical engineering, product testing, plant automation, software product and platform engineering, is one of the three main pillars of HCL. And we cut across multiple verticals, be it aerospace, automobile, industrial manufacturing, medical devices, office automation, telecom, consumer electronics, ISV and online, and semiconductors. For past 5 years, we have continuously growing with roughly 10% CAGR. And our presence mostly centered around Americas, with 63% of our clients being in that geography, followed by in Europe and then rest of the world. HCL by itself is a pure play company, which means we focus mostly on client services and low volume manufacturing. Right. But if the need be, we can also have partners who can help us help the clients in taking the product to high volume manufacturing. We also invest heavily in research and development through what is a concept called Center of Excellence, or COEs, which helps the client to offload some of their research and development to HCL, and then we come up with the right solution for the clients. For example, very recently we opened a COE for quantum computing because quantum computing has become one of the hot areas today, and we wanted the clients to help. We wanted to help the clients into quantum computing area, and so we created a COE just for the quantum computing. We have also been awarded as a leader in semiconductor engineering by Peak Metrics, and we are one of the world's best employer according to Forbes 2021. So this slide tries to capture what HCL can do in the chip design domain, because the main topic of today's discussion is chip design. So if you look, HCL has presence in almost all the domains of chip design, starting from architecture, right? So we can architect, just given the spec, we can find an architecture for the ASIC, and then we have a stream which focuses on analog circuit design, their schematic capture, layout, mixed signal verification, IP customization. And we also have the entire digital flow where we take the concept, put an RTL design, do functional verification, validation, synthesis, packaging, right? And then for a small volume, when we are having a small volume manufacturing, we also have partnership with a couple of MPW partners who can help us in getting the test parts for fabrication. And then once the parts come back, we have a full set of lab which can do board validation and characterization and testing of the finalized or produced part. Right? Apart from this main infrastructure, we also support the peripheral practice areas. For example, CAD, EDA, IT, memory development, emulation, simulation. We also can do hardware prototyping, also if the need be, packaging design, not just packaging of the ASIC, but let's say if the product is mechanical packaging, that also could be designed by HCL team. And like I said earlier, it's a pure play company. So it's up to the customer of what all services they want to avail from HCL. It could be just one of those, for example, just the IP design, or it can be end to end where they provide a spec and we just give them the final product. Yeah. So this slide captures more of our expertise into the semiconductor area, and we have experience into wide varieties of foundries which manufactures semiconductors, and across multiple nodes. So if you see, we have experience all the way down to 3 nanometer, which is emerging node today. And on the other end, we also have experience in higher nodes like 180 nanometer, 130 nanometer, which are very popular for power management kind of application. And again, we have experience with multiple foundry, be it leaders like TSMC, Intel, GF, UMC, Towers, Samsung, and ST, and across various of their foundry nodes. So we have done design of SerDes, power management chips, I/O data converters, clocking solution, digital SoCs, analog SoCs, mixed signal SoCs for into multiple of these nodes. And apart from these, we also have a lot of direct connect with the foundries. For example, with TSMC, we are DCA member, and we have an advanced node two-way NDA, which allows us to quickly get access to any of their advanced node PDK. We also offer ODC and clean room. With Global Foundry, we are ecosystem partnership, and then we have access to their all the PDKs up to GF12LP. With Samsung, again, we have direct connect and we can access any of their PDK up to 28 nanometer. And we also have worked on to their smaller nodes like 14, 5, and 4. Okay. Apart from that, also, since we work with multiple of these foundries, we have direct connect with UMC, TSMC, Tower, TSI, ST, Dongbu, and we have done multiple of these IP projects into these foundries. So, focusing mostly on the design bound standards, this picture tries to capture the essence of the requirement. Now, standard IPs which are available in the market, right, are a great way to start a product. They help us in reduce the overall turnaround time. It simplifies the ASIC integration. But there are many instances where the standard IP which is available doesn't fit the requirement. It could be just because the IP aspect ratio doesn't meet the ASIC requirement. It could be because there are some functional parameters which are not meeting the design target. Or it could be just because the standard IP does not cater to the extended requirement from the customer. When this kind of scenario occurs, customer has two choices, right? Either they can take the IP as is, whatever is available, and try to modify their ASIC so that they can fit the standard IP into their product, or go ahead and start designing from scratch so that the IP fits their requirement. In both the cases, it's a cumbersome process because in one place we are compromising on performance, in another place we are compromising on schedule. So IP as a service is a way of bridging this gap where we have some way of some IP to start with, or we need some IP. At the same time, we don't want to spend that much development effort from customer side. So that's where IP as a service comes into the picture. Now, it could be either we start with an existing IP, like I said, standard IP, we take that IP, modify it so that we can meet the customer requirement. Or it could be just a fresh development of IP because the standard IP may not even exist. With IP as a service, the burden on customer goes down because it is one possible way, one reason could be because the customer may not even have the expertise into developing the IP which they need. Like for example, let's say if the customer is focusing on power management and the requirement for is for a SerDes IP, customer might not even have enough expertise to develop the SerDes IP. And the other reason could be that customer does not want to spend their resources into developing an IP which they might not need down the line. Right? So this IP as service allows this flexibility to outsourcing the IP development to companies like HCL. So what we'll do is we'll look at a couple of the case studies which shows how IP as service can help customers. So the first case study which is here was a development of a combo receiver, which was to get data in a C5 or D5, MIPI C5 or D5 protocol. Now this was targeted for a tester application. Right? So the requirement was to go beyond the specification of MIPI C5 D5 because we want to do compliance testing of the device under test. And this was required at a little higher node, like 55 nanometer. The target was to support the C5 1.2 and D5 2 specification, which operates roughly at 5 gigabits per second. And then since it was only receiver, it was also required to give all this data back as an LVDS output because it was then further processed into an FPGA to make sure that the device under test meets the compliance. So for application like this, there was no off-the-shelf IP. One possible option was to use two independent C5 D5 IPs and then put them on a IC. But customer was having problem with that, and so they decided to develop the new C5 D5 combo IP. And there was specific multiplexing was required between the pins. It was expected to tolerate larger rescue because it was expected for a tester application, so it has to go beyond the specification. So to do something like this, we created a programmable high-speed receiver. We created a CDR, which was based on coarse and delay tuning. We created a 8-bit interleaved LVDS IO so that it can meet the customer requirement. And then we added a JTAG and BIS so that we can do the on-chip testing of the IC. And eventually, we delivered this GDS along with test plan, test vectors, validation report, and performance report. And the part is silicon proven and now is part of one of the largest tester company application. Another such example is Displayport, which is EDP receiver for a chip on glass application. So the chip on glass application offer very poor medium for transmission. And the requirement was to support a QHD display, which is 2160 by 1440 display. And the target was to support up to 2.7 Gbps link. And there was no off-the-shelf IP available because the IP typically target for a PCB channel, and the glass was very poor for that medium. It also had very high supply noise, again, because the glass is a poor medium of conductance. And there was, on top of it, there was these connectors and cables, which was adding on top of the loss. So we had to design an equalizer, which was way beyond the spec required by the EDP. And then we also improved the supply immunity of the receiver up to 100 millivolts. And we added BIST and loopback so that we can do the testing of the IP on ASIC itself. And since it was an IP development, we delivered the IP along with test plan, vectors, and the integration guidelines. And this design is now silicon proven and is part of one of the Lenovo's product series. Another such scenario occurred when customer was looking for a combo IO between DDR1 and DDR3. So typically DDR1, 2, or 2, 3, or 3, 4 are common, but finding a combo IP which supports DDR1 and DDR3 was not possible. So again, like in the previous case, they had option of putting one entire DDR1 and DDR3, but that was also going to consume a lot of area and power. So what we did was we created the combo IP with 1.8 volt device, because that was one of the problems. The device available was only 1.8 volt, and there was large input variation because of DDR1 and DDR3, and also again large supply variation because one operates at 2.6 volt while DDR3 was expected at 1.35 volt. So again, we took the specification and we created the programmable impedance calibration driver. We supported up to 800 megabits per second DDR speed. And then because it was a large shelf life product, we also supported 10 years stress testing for ESD and EMIR. And because we developed the IP with a combo, we all were able to optimize area as well as power to support both the protocols together. And with this IP, we again delivered the IP along with test plan, vectors, integration guide. And this is silicon proven IP, and it is now part of HP printer product. So this is a similar example as the previous one. Here, the requirement is developing a combo IO which supports I2C and I3C. So I2C and I3C combo IO is not readily available in market, and the target was to support I2C in FM and FM plus mode, while I3C in open drain and push pull mode. And then it was also expected to have a bidirectional buffer. Right? So apart from the standard I2C interface, it's also expected to behave like a standard GPIO and support 200 megahertz at 10 peak of farad of load. This kind of IP was not available. And since the devices available were only 1.8 volt and the target was to support up to 3.6 volt, we had to create an over voltage and over voltage tolerant and fail-safe IO. And then the requirement was to support voltages anywhere from 1 volt to 1.8 volt. So here we came up with an innovative design to support the fail-safe and then over voltage for the combo IO. And here again, we did a 10-year stress testing for EMIR. And then since we were developing the combo IO and not just taking two different IPs and putting them together, we were able to again optimize power and area. So with this IP, again, we delivered hard IP along with test plan, vector syndication guide. The design has been taped out now and we are waiting for silicon results. Some of the other examples of customization we did was, for example, this was an LV CMOS IO. This LV CMOS IO was expected to have a slew rate control from 0.09 volt to 0.96 volts per nanosecond. But the same IO was also expected to work as LED driver, which two are very different requirements. And the challenge came because in the driver mode, it was expected to drive 5 feet of a long cable with 20 picofarad of load. And in the LED mode, it was expected to drive a 16 milliamp load because the LED was consuming that much current. So here, what we did was we started with a standard LV CMOS IP, and then we modified it so that we can add PVD tracking for slew control because the slew control range was large. And then on top of it, we added a programmable current driver so that it can also behave as a LED driver. Another such example is LVDS IO. So this LVDS IO was standard LVDS IO, except that the requirement was to support IO swing, which is beyond the triple E spec of 400 millivolt. And in this scenario, the issue was because we are supporting larger swings, and at the same time, we did not want to compromise the data integrity because the swing was beyond the specification. So we created a swing optimized bias, and then we added also supply tracking output driver so that we can support the large swing requirement from customer, which were beyond the IEEE spec. Another such example was in the soft IP of I2C MAC. So typically I2C MAC comes with acknowledged signal, and that is what has been used across the industry. But in this particular case, customer also wanted to add a not acknowledged signal, which is not part of a typical I2C MAC. So of course the challenge was to modify the IP so that we can support both ACK as well as NAC signals. And then we added this feature on top of the existing IP, and then we verified it for asynchronous operation so that it meets the standard I2C compliance. On top of it, when the customer wants it, they can also use it as a NAC signal. Right? So as you can see from previous case studies, IPaaS service is a very good offering for customer who don't want to spend their resources on developing a new IP, or who do not want to compromise on the specification with the standard IPs. Pure play companies like HCL have multiple domain knowledge, and which comes very handy in IPaaS service development, because we understand multiple IPs domain, and then we can develop IP based on the customer requirement. It's not limited to just one particular domain. And apart from this, since the companies like HCL have a wide partnership and ecosystem network, we can directly work with foundries to get PDK, which will reduce the overall turnaround time. We can also work with IP vendors to get their standard IP and optimize it for the customer needs. And we can directly work with EDA vendors to get the tools required for developing such IPs. So by offering IP as service, customers do not have to settle on an ill-fitting IP, and they don't necessarily have to spend their valuable resources on an IP development, which may not be the area of their expertise. So by offering such services, IP as a service, the customer can leverage their core expertise into developing their EC and can outsource all the IP development to companies like HCL. Thank you for your time.